Hello class, and welcome to lesson 2.3, stretches, compressions, and reflections. So last day in class we dealt with the C and D values of the translations, which do your horizontal left-right movement or your shift phase, and then your vertical shift, which is your up and down movement. Today we're going to add in the A and the D, which deal with stretch, compression, and reflection. So let's apply it to what we should know, which is our quadratic function, since we did a lot of that from grade 10 and some into grade 11. All right, so we know we start with our parent function, ladies and gentlemen, which is your basic 1, 3, 5 step pattern. So that's your base or parent function. Okay. Notice what's different now is the letter is out front. Okay, so in our second example, folks, A equals 3. And A deals with your vertical stretch or compression. If you take a look at that, it's going to make it a little narrow, okay, because A is 3, so it's going to be stretching. If you take an elastic and you pull it from the top and the bottom 3 times the force, then you're going to make it narrower. All right. Likewise, ladies and gentlemen, the next one, 1/3 is what A equals. That means instead of having a regular force, you're going to have a third of the force, which means you're going to make it flatter, like a pancake. Okay, so it's going to widen up. Notice the difference in our next example, ladies and gentlemen. We have the 3 inside the bracket. So what does that tell us? K equals 3. You should remember that when you have a factor, it's going to be a factor of 1 over the absolute value of K. So therefore, the factor equals 1 over 3. Okay, and when you put that in, now instead of shifting from, so if we back up for a second, this stretch was from the up and down movement. Okay, for B, or for the third part, we were pushing it from above and below. But now that we've got the K factor, ladies and gentlemen, the K is having us come in from the side. So in this case, we're pushing in this way. And so what does that tell us to do? We make it narrower. Okay, so what do we call that? We call that a horizontal compression by a factor of 1/3. Lastly, we have K equals 1/3, which means if you put it into the factor of 1 over 1/3, you flip that, ladies and gentlemen, which equals a factor of 3. So by doing so, what we're actually doing is pushing it away in the horizontal direction, and we're making it flatter. Okay? So hopefully you recognize the transformation formula from grade 10, same as last day when we did warm-ups. But this day, today, we're going to take a look at the A and the K. Okay? So the A, if A is negative or less than 0, I'm going to write down negative here because that's easier for people to remember. Just remember, guys, that it reflects the x-axis. Okay? If the absolute value of A, okay, is between 0 and 1, we have what's called a vertical compression. By a factor of A. And if the absolute value of A is less or greater than 1, folks, we have a vertical stretch. You may be asking, hey, Mrs. R, why do we deal with absolute values here? Just remember, folks, if it's negative, that takes care of the flip. Then we're just worried about the, so the sign tells us we're reflecting the x-axis. It's the value that tells us how much we're stretching or compressing. All right. Now we're going to take a look at the K value. Okay. Again, if K is less than 0 or negative, this is the tricky one. It doesn't reflect the x-axis, it reflects the y-axis. Okay. And if the absolute value, again, the same sign situation here, we have absolute values here. Okay. Let me just back that up a sec. So the absolute value of k, if it's between 0 and 1, because the negative sign tells that it reflects, we have a horizontal stretch. And don't forget, it's by a factor of 1 over the absolute value of k. Okay? Likewise, if the absolute value of k is greater than 0, we have a horizontal compression. And again, it's by a factor of 1 over the absolute value of k. All right. So if you thought that was pretty strange dealing with a and k's with quadratics, we're now going to apply them to sinusoidals. So basically, if we're doing any stretching or compressing, we're going to change the period. And if we're reflecting, then we're going to change the way things look. All right. So let's give that a try. And again, we're going to use a graphing calculator. So you're going to need some colored pencils or pencil crayons like we did yesterday. So again, we're going to go to our calculator, make sure it's in degree mode. I should have it up here running. Let's double check. Press mode. Yes, it's in degree mode. Let's check our window. The window settings are exactly the same as last class. However, when I press y equals, I have some graphs in here. So let's clear these out. Okay. And we're ready to start. So the first graph we're going to take a look at, ladies and gentlemen, is y equals sine x. Just remember, how do we start the sine x curve? We start, my fault, we start at its axis. We go to its maximum, axis, minimum, maximum. Sorry, axis, my fault. Okay. So you've got a lovely sine curve. The more you practice drawing these, the easier it gets. Okay. Okay. And we're going to deal with the a value first. So the a equals 1. What does that mean? My maximum right now is 1. Let's see what happens on our next example. A equals 2 sine x, so that's out front. So let's go to our graphing calculator, go sine x, get our first one up. Okay. And then we're going to, my fault, let me just back that up. Sorry, let's clear that. Go up, and we'll go sine x. Put it in the front, and then go down below, and we'll change that to 2 sine x. All right, I like to always make my second one look a little different by, I'm sorry, I got to put my ink layer down. Sorry, give me 1 second. I'm going to cancel that. Sorry, that was not good. I almost lost our lesson there. So here we go. I'm going to change that thicker. Okay, now let's graph these and see what happens, folks. So again, here's our parent function of sine x. And then what's going to happen now? So notice what's happening. The axes are the same. So where they hit the axis is the same. But instead of going up to 1 as a maximum or down to -1 as a minimum, they're reaching a maximum of 2 and a minimum of -2. Okay, so let's go to our graph and graph that. Okay, so our axes stay the same. So I draw them in, but our minimum or maximums are twice as big in either direction. Okay, so draw a smooth curve. I find it actually gets easier to draw these smooth curves the bigger the amplitude is. Okay. So again, we notice here, guys, A equals 2. What does that mean? We have an amplitude of 2. The third one, looking at it, what's my value of A here? Some may say 3, but it's -3. So 3 means that it's going, instead of have a maximum of 2, it's going to have a maximum of 3. But the negative means to flip it above the x-axis. So as we start at 0, we're not going to reach our maximum first. We're going to reach our minimum first, okay? Because it's negative. Again, let's go back to our graphing calculator and help us discover that. So go to y equals, leave sign x as is, change this to negative, and you need the negative button, not subtract 3. Okay, so negative 3 sine x, graph it. So here comes our parent function. And then what do we notice? It's the opposite. So see, from the origin, we go to its minimum as opposed to its maximum as we increase. All right, so let's graph that. So again, the axes are the same, but we're doing the opposite. Okay, so wherever it's a minimum, it's going to be a maximum. Wherever it's a maximum, it's going to be a minimum. All right. So again, draw a nice smooth curve. All right. Kind of cool looking, eh, guys? All right. That's dealing with the sine function. Let's try doing some with cos. Again, with cosine, we start our parent function at its maximum. Then we go to its axis. Then we go to minimum, axis, and maximum. If you can develop those patterns, ladies and gentlemen, it'll be very easy for you to draw. Okay. So that's our cos x. So let's go plug that in. And what can we make as a prediction here, ladies and gentlemen? A equals -2. The negative tells us we're going to do what? Flip it or reflect the x-axis. And the 2 tells us we're going to have an amplitude of 2. So in this case, folks, instead of starting at our maximum, where are we going to start? At our minimum. And the minimum value is going to be -2. Let's use a graphing calculator to show that, folks. So go to y equals, clear your second fraction, and change that to -2 cos x. Go up to the first one and change it to cos x. Okay, so has everybody got those ready? Okay, press graph. Here's our parent function, cos x. And in comes our transformation one, okay? So notice when we have the A, the shape changes. It gets larger or smaller, and the A also can invert it or reflects the x-axis. All right, let's graph that now, guys. Okay? So what is similar, folks, is where it meets at the axis. They stay the same. Okay, but what's opposite is the minimum versus the maximum, okay? All right, so draw a nice smooth curve. Make sure you have arrows on both sides. All right. Let's try this third one here, and then we're going to get into making a summary here. So A equals 4. So what do we know, folks? It's positive, so we're going to start at our what? At our maximum. And our maximum value is 4. So we're going to start there. And our minimum is going to be -4. Let's try graphing this first, and then we'll use a graphing calculator to get it. And I like when you have a big amplitude because I find it's easier to draw these big sine or cosine curves when you have higher amplitude. So looking pretty cool, eh? Nice design. Some people might like that for a tattoo. All right, let's check that out here on our graphing calculator. So leave the first one there, and then let's change that to 4 cos x. So press 4 and delete. Okay, try graphing that. So here comes our parent function. All right, let's develop some summary here with the A value. Okay, so what can we conclude about the A in A sine of x and in A cos of x? Well, first of all, if the absolute value of A is greater than 1, we know we've got a vertical stretch, just like on the warm-up. Okay, if A is less than 0 or negative, what does that tell us? It reflects x-axis. And if the absolute value of A is in between 0 and 1, we know that we've got a vertical compression. And if you need those arrows to help you think about it, vertical compression pushes inwards from the vertical, but the vertical stretch pushes them out. Okay? And what we should have developed here, guys, a new thing is that the amplitude equals the absolute value of A. All right, let's deal with that tricky one called K. Okay, one thing I want to introduce to you is how we can relate K to a period. When the period is the length of time it takes to complete one cycle in a wave or in a function of sinusoidal. So a period, ladies and gentlemen, equals 360 degrees, because that's normal, divided by the absolute value of K. That's going to help us decide how to deal with this horizontal stretch or compression. So all along, ladies and gentlemen, we've had our nice sine wave and cosine wave functions all being done in a period of 360 degrees. That's now going to change because of the K factor is going to have an impact on that. All right, don't worry, we can do this together. All right. So first of all, let's take a look at our parent function. In our parent function, K equals 1. So what does that tell us? That when you take a look at sine x, same as what we have before. Nice smooth curve. Okay. Now, looking at the second example, ladies and gentlemen, it's a little more interesting. What do we notice our value for K is? K equals 2. So if I plug this into the formula here, I'm going to have the period equals 360 divided by 2. So my period in this case is going to equal 180 degrees. So what's going to happen is I'm going to have to draw a wave within 180 degrees as opposed to 360 degrees. Before we draw that, ladies and gentlemen, let's take a look at how the graphing calculator looks, because it'll provide hopefully a better understanding. So let's go back to our y equals. Let's change that to sine x, and then we'll go down here and we'll change that to sine of 4x. My fault. Which one are we doing? My fault. 2x, not 4. 2x. Everybody good with that? I'll just clear these keys so if it's not bothering people. All right, so let's press graph. Again, we'll see our parent function as it regularly is. And then here's where the tricky part comes. Notice what's happening. To complete one, it takes half. It's completing it twice as fast as the regular one. So see how in the time it takes to do one parent function, we have 2 of the transform functions. All right? So taking a look, ladies and gentlemen, with our sine curve, it takes 360 degrees regularly, but as soon as we add a K factor that's not 1, it's going to make us have to do this in different time intervals. So for example, instead of getting 1 from 0 to 360, we need to have 2 complete cycles. Okay, so what does that mean? that means that we're going to be going like this. Okay, so this is probably the hardest one to grasp, ladies and gentlemen, in that we need to have 2 in the time that we would normally have 1. Okay, so hopefully you can draw that in. And again, put your arrows on. All right, let's try the third one. This is a tricky one too. Okay, looking at the third one, k equals 1/2 or 0.5. Okay, if you try to find the period for this one, we know that it's 360 divided by 0.5. So the period's going to equal 720 degrees. So instead of completing one cycle in 360 as the parent function does, it's going to take us twice as long to do that. Okay? So let's go to our graphing calculator and compute it before we draw it. Okay? So we just go 0.5x. You guys with me? Take a look at this one. So here's our parent function. And wow, take a look. So it takes our whole screen, ladies and gentlemen, to do what? To get one complete wave, even though we're saying half of each because our starting point is still at the origin. All right, so let's go graph that. So we're going to start here, and we need half of our wavelength to be in the quadrant 1 here. So half is going to be here. So you're going to go half there. And then we have to show in the other half, we have to show the minimum. Pretty funky graphs, eh, guys? All right. Let's try doing some with cosine. Okay, so let's remember our cosine curve regularly where k equals 1. Those are nice because you start at its max, go to its axis, min, axis, max. Okay, so let's draw a smooth curve. Put your arrows on. All right, so if we know k equals 1, that's sweet, that's nice. It takes us 360 degrees to complete one cycle. Let's try the second one. K, in this case, equals 3. So instead of having one cycle in 360, we need to have how many? 3 cycles within 360. Okay? So we've got to figure out how we're going to do that. Okay? All right. So let's take a look at that. So what we need to remember, folks, is the period is 360 divided by k. So 360 divided by 3. So the period equals 120 degrees. All right. So with 120, we've got 90, and 45 is 120. So just about in here. And then 240 is right about in here. I'm looking for 240 here. It's 220, about 240. So within each of those, we're going to have to draw one. However, let's go to our graphing calculator and get a visual for that to help us. Oh, sorry, ink layer's up again. Okay, let's try that again. So let's go to y equals, change that to cos x. Okay, down below we're going to go cos 3 x. Okay, everybody got that? Okay, let's graph it, see what it looks like. So notice that in the time to get 360 degrees, we have 3 cosine curves. Okay? So what does that mean? If you take 360 and find 120, I'm going to have a maximum here, I'm going to have a maximum here, a maximum here, and a maximum here. Okay? So within that time frame, we're going to go woo, woo, and woo. Okay? Do the same on the other side. So we need roughly 100, negative 120, negative 240. So that's where our maximums need to be. Okay? So we're going to swoop down, come back up, swoop down, come back up, swoop down, come back up. Okay. All right. Let's try the next one, or the last one. Y equals cos of 0.25x. So k equals 0.25 or k equals 1 over 4. Okay. If you put in a period equals 360 divided by 0.25, and that's going to be a lot. It's going to be 1440. So what does that mean, ladies and gentlemen? That it's not even going to be able to do one movement within 750. We're only going to have half a movement within our whole, 720. We're only going to have one movement within our whole graph here. Let's take a look at our graphing calculator. Plug her in. So got the parent function, leave it as is, and we'll just sub in 0.25x. Okay, let's give that a graph and watch this. So again, we're only really showing a complete half of the cosine curve. Okay, so we're going to start here, and it's only going to get to its axes at the end. Okay. All right, so let's make some conclusions about our lovely letter K. So if the absolute value of K is greater than 0, okay, we know we're going to have a shorter period. Okay. Whereas if the absolute value of K is in between 0 and 1, we know we're going to have a longer period. And we're going to remember, and hopefully you have this one toolkit you want to remember or memorize it, is that the period equals 360 degrees divided by the absolute value of K. Okay, ideally, folks, the great thing would be if K, absolute value of K equals 1, okay, then the period equals 360. That's what we were doing all previously. That's what we call normal. Okay, and the last thing, and hopefully we don't have too many cases of this, if K is less than 0, that means it reflects the y-axis. Okay, so it reflects the y-axis. All right, one thing I want to make special note here before I change this is that some cases you're going to have to find the absolute value of K. So K actually equals 360 divided by the period if I just rearrange that equation. That's going to come up, I believe, next class or the next 2 classes. So there's something to have you spotted that you can recognize that. All right, here is a summary, ladies and gentlemen, that you should copy down if you haven't already got these things figured out. Okay, what happens to A, folks? If A is between 0 and 1, you have a vertical compression. Okay, and I'll put my arrows in for that one, ladies and gentlemen. Okay, if absolute value of A is less than 0, you get a vertical stretch. Which means they're going out. Okay, if A is negative, it reflects the x-axis. Okay, looking at K, If k is between 0 and absolute value of k is between 0 and 1, you've got a horizontal stretch, okay, which means we're stretching it out this way, okay. And if we have a compression, then we are going to, I apologize, just give me 1 second. I've got these things confused. So I'm just going to change that for a second. Let's take a look here. If k is negative, it's less than 0. If k is greater than 1, you're going to have a horizontal compression, which means, yes, you're pushing him this way. And the horizontal stretch, I just had that backwards. Sorry, guys. There we go. All right. So new things we should remember and put to memory is that the amplitude is the absolute value of A. Your period is 360 degrees divided by the absolute value of K. And now that we've dealt with A, when we take a look at our range, it's our minimum to our maximum. So our maximum, our minimum, equals our C value, subtract the absolute value of A, and our maximum equals C plus the amplitude. All right, C we discussed yesterday, and C is your, just remember, last day y equals C is your axis of symmetry or axis of equation, and the other thing we learned was that D equals starting point. So now we've got them all taken care of. Okay, let's take a look at the transformation question here. Okay, so looking at this, and this is our last example before we do homework, identify the transformations, then state the amplitude and the period. Okay, so looking at this first expression A, the A value in the transformation is 0.5. What does that tell us? We have a vertical compression by 1/2. Okay. We also note that K equals -3. That means it reflects the y-axis. And it means that there is a horizontal compression. Okay, by, and don't forget to put it in the 1 over absolute value of K, so it's going to be by 1/3. Okay. So those are the basic transformations. There's no C or D part because C equals 0 stays at the axis stays on 0, and D equals 0, which is your starting point. Okay, now it asks us for the amplitude. Amplitude equals the absolute value of A, so amplitude equals 0.5, and your period, put it into that new formula you learned, equals 360 divided by your absolute value of K. So again, it's -3, but absolute value of -3 equals 3. So your period is now going to be 120 degrees. All right, last question, folks. In this case, we've got A equals -5. That tells us it reflects the x-axis. The 5 tells us it is going to be a vertical stretch. By a factor of 5. Okay. K equals 0.25, which equals 1/4 if you like to deal with fractions. And that's going to give us a horizontal compression by 4. Okay, so in this case, when they ask for the amplitude, it equals the absolute value of A, so it equals 5. And your period, which is similar to what we did in our lesson, is 1,440 degrees. All right, folks, that's as hard as it gets when it comes to transformations of sinusoidals. We just have to put them all together now, and then we're going to work backwards. Eventually, we're going to be giving you graphs or explanations of transformations, and you're going to have to come up with the equations. So again, if you're having some struggles with this, please come and see me before we put it all together and before we have our quiz and our test, okay? Here's your homework today, page 31, 32, 1A, B, 2AB, 3A, B, C, D, and 7 and 11. Have a great day and hope to see you soon. Hope and come see me if you need help. Okay? Bye.